Welcome, everyone. Pleased to have you here with us today for episode 93 of This is CDR. This is CDR is an online event series presented by OpenAir to explore the range of carbon removal solutions currently being researched, developed, and deployed, and to contextualize them for policy proposals OpenAir seeks to advance here in the US at every level of government, as well as in national and subnational jurisdictions globally. My name's Toby Bryce, based in Brooklyn, New York, and I work on policy advocacy and market development with OpenAir. If you haven't done so already, please say hello in the chat, introduce yourself, your affiliation if you'd like, and where you're zooming in from, and make sure to direct that message to everyone, not just host and panelists, so that everyone can hear from you. Quick background on OpenAir. If you're not familiar with us, we're a distributed all-volunteer network dedicated to the responsible advancement of CDR. We are a global community. We work together on shared open source projects that we call missions in the areas of policy innovation, communications, and activist market development. Here's a sampling of the projects we have going. We have a few dozen active projects, and we are always spinning up new ones. If you join our group, my colleague Megha is running the Zoom chat, and she put a couple links in there where you can fill out a form and join our organization. If you join our group, you can start your own projects. You can sign on to an existing project. Again, it's open source, and we, are really just working together to try to drive impact and again, accelerate and advance the responsible deployment of CDR. One project that's at a critical juncture that we have going is a state-level CDR procurement policy in the U.S. state of Massachusetts, S2096, the CDRLA in Massachusetts. And if you live in that state, please reach out to us. We need all the help we can get in terms of citizen lobbying, contacting your local representatives, et cetera. And so if you are in Massachusetts, please give a shout, and we'd love to connect with you and see if you can get involved in some of our advocacy efforts there. Before we get started with the program, as always, a quick definition of our terms here. This is a definition of CDR from a great resource called the CDR Primer. I will put a link to that again in the chat. Purposeful human activity to remove CO2 from the atmosphere and durably store it in geological, terrestrial, or ocean reservoirs or in long-lived products. This is also essentially the same definition that the IPCC uses, and we think it's a good one to work with. Before we move on, we always have to disclaim loudly, clearly, upfront, multiple times that CDR is in no way, shape, or form any sort of substitute for reducing emissions. We need to rapidly reduce global greenhouse gas emissions and decarbonize the economy. We need to do this as quickly and as completely as possible. It's the significant majority of the climate work we have to do over the next couple decades, like 90% plus. That said, there's clear scientific consensus that we also need CDR in parallel. We need to start building the capability to remove billions of tons of CO2 from the atmosphere by mid-century. And the reason for that is that we're not going to be able to completely decarbonize the global economy. We're not going to be able to reduce all of our hard-to-abate emissions by mid-century in a climate-relevant timeframe. So those remaining residual emissions need to be neutralized with high-quality, long-duration CDR. Then in the second half of the century, we're going to have trillions of tons of anthropogenic CO2 in the atmosphere. Our climate, as we see daily in the news, is already at an unsafe state. And so we're going to need to be able to have the capability to remove CO2 from the atmosphere at very considerable scale in the second half of the century to restore our climate to a safe state. So CDR is essential. It is not a substitute for reducing emissions. We need to keep our eye on that focus, but we also need to start building the capability to deliver CDR at massive scale by mid-century. And that's why we're here. So I'm going to hand it over to my colleague, Megha, who's going to talk a little bit about run of show, and she is going to introduce today's speakers, which we are super excited to hear from.
Hi, everyone. I'm Megha. I'm an OpenAir member, normally based in London, and I work on policy and market development as well. So some housekeeping notes before we begin. We're going to start with a short presentation, followed by a few prepared questions, and then moderated audience Q&A. So please type any questions as we go along into the Q&A box, not the chat box. It does help us to separate and organize them if you just find the right box to type it into. So please just make sure that you do that along the way. The event's also being recorded, so we'll post the recording to our OpenAir's YouTube channel and OpenAir's website. We will also send it to everyone who registered, so you'll have that in your inbox as well. All right, this week we're very happy to welcome Rory Brown and Jasper Wong from Airhive to present and discuss the company's novel DAC process, which employs fluidisation to dramatically accelerate the mineralization of atmospheric CO2. Rory Brown is the co-founder and CEO of Airhive. He is an experienced manager and strategist who has delivered over £200 million in overseas programs for the UK government, and Rory brings leadership and delivery expertise to rapidly scale Airhive's technology. Jasper Wong is co-founder and CTO of Airhive. He is a PhD research engineer from Imperial College London with a background in decarbonisation. He holds a BA and Masters of Engineering from the University of Cambridge, and he brings scientific and engineering expertise to Airhive's technology. So when you guys are ready, please go ahead and come on and start with your presentation.
Thanks, Megha. Hi, everyone. Very nice to speak to you all today. So we're going to just dive straight into the technology. As I guess many people with the good introduction from Toby understand the why. So we'll just get straight into the what and the how from our perspective. So over to you, Jasper.
Yeah, nice to be here today. So it's a pleasure to introduce Airhive. Our technology is based on a phenomenon known as fluidisation. So fluidisation is a physical process. It's been around for a long time. It's used in a whole bunch of industries, from drying salts, drying spices, to cement, iron, and steel industries. And essentially what happens is you have an upflow of gas, in our case air, which flows from beneath into a solid sorbent mixture, and creates almost like fluid-like behavior. So the mixture of the gas, air, with the solid creates almost like a bubbling fluid-like behavior, or what we term it as almost like a sandstorm in a contained reactor system. So the reason that sort of sandstorm effect is very interesting is you create very rapid mixing between the solid particles, which we use as natural minerals, which are very quickly in contact with all of the gas, the air passing through the system. And therefore, the solid sorbent material, which likes to bind with the CO2 in the air, is able to very quickly bump into all the CO2 molecules passing through the system. So we're able to capture the CO2 passing through our capture system, which is on the left here. So I guess the key innovation is that we're able to pass air through our system with fans and remove all the CO2 passing through it in a residence time of less than 0.1 second. So the amount of time that the air is in our system is less than 0.1 second, and it comes out as nearly 100% clean. So our fluctuations on the gas measurement are between 0 and 10 ppm, so very close to 100% CO2 removal. We use a two-step process. So I've spoken about the carbonator, which is the capture stage. Once the sorbent mineral is saturated in CO2, it moves to the calciner, where we use renewable electricity to heat up the sorbent to about 800 degrees, at which point the CO2 desorbs from the mineral, or unbinds from the mineral, is released in a pure form where we can durably store it. The calciner, we do that in the presence of steam. So we also fluidize in the calciner, so that creates very quick mass transfer and also heat transfer in that system, which means we're able to decrease the desorption temperature and improve the kinetics of the calcination. And calcination is the removal of CO2 from the sorbent material. Finally, the sorbent material, after it's been calcined or unbinded the CO2 from it, we return that in a closed loop cycle back to the carbonator. So that's the final step. So yeah, I guess the key innovation for this is improving the speed of the actual chemical reactions involved for the capture and the calcination, which directly translates to the equipment sizing. So by having very, very high throughputs through the carbonator system, we're able to decrease the amount of equipment we need for a certain throughput of air and therefore CO2 captured, which translates to capex costs as well as land footprint. So it means we're able to have a very capex efficient and also small land foot system with really good energy profiles as well. So go to the next slide, please. So in Q3 this year, we're excited to be piloting two systems at 1,000 tons per year, one of which is with Deep Sky, a Canadian project developer, where we'll be deploying using hydroelectric power, and then a second 1,000 ton per year system in a utilization partnership that we'll be excited to announce later this month. And so here we've got a render based on actual manufacturer's design. So you can see the equipment we're using is rectangular, relatively modular, although we hope to, in later mechanical designs, to make this look more like shipping container modules. These are our first pilot designs. So in the system on the right, we've got the carbonator. That's where we blow air from below, and we capture the CO2, and then we have those air chimneys, which releases the clean air. And then we have the solid material transferring to the calciner, or where we desorb the CO2 from the sorbent mineral electrically. So essentially what we're doing is speeding up the mineralization process, which is a natural earth process. So carbonate minerals carbonate over time, over thousands of years. And what we try to do is make that happen in a much accelerated time frame, so in minutes and hours. And we try to do that using a renewable electricity as well. We can go to the next slide. So we've got a short video here which shows a nice little video of fluidisation. So you can see here we've got the particles. And what's interesting about fluidisation actually is you could, even though you've got a mixture of a gas and a solid, you could put a rubber ducky on the sorbent material, and you'd have a sort of floating rubber ducky, just like it was in a bubbling fluid or liquid. So it's really quite an interesting phenomenon.
I'll play it one more time just for benefit. So yeah, on the right, obviously, this is the carbonator. So that's what fluidization would look like in practice in that quite small reactor vessel, on top of which is mostly filters for any small amounts of sorbent that is lost, ground up, into smaller particle sizes. And then that one is the calciner, out of which you would then get the pure stream of CO2. This slide. There we go. Yeah. Yeah. So I think maybe just to step back a sec. So we formed in summer 2022, and it kind of at that time we sat down and we thought, what are obviously the key characteristics that we need to solve for? And at the core, widely understood, if you look at IPCC, AR6, chapter 12, say DAC as one of the profiled carbon removal technologies or methods, as they call them, cost and energy. That's kind of, I guess, should be obvious to people listening who have a knowledge of removal, that those are really the key challenges. We sort of add another one, which is deployability, scalability. So, those were the three things that we really wanted to solve for. How do we drop the cost, have as energy efficient a process as possible, and have something that is ready to scale quickly? Jasper mentioned the sort of very fast removal, and the fact that we're using effectively quite widely available equipment. So we're talking about, manufacturers all over the world produce thousands of fluidized beds every year, from quite small ones to ones that are 80 meters high. There's a lot of sort of process knowledge, engineering knowledge out there for the use of fluidized beds. So the very fast removal and the fact that at its core, it's not an overly complicated equipment means that, we really push the kind of capital equipment costs down. And just to sort of put a number on that for these pilots coming up, the sort of capital costs for the core equipment, standing aside the kind of installation of some of the site prep, is sub $70 a ton. And the fact that it's well understood technology means that sort of manufacturing ramp up is easier. So for us, really, the sort of big inventive leap was proving out that first 4 technology readiness levels. It's the science bit. We're able to move. We've got very good sort of tailwinds, able to move quite quickly through the engineering bits, because we've been able to work with manufacturers who've been able to come up quite quickly with designs that are very different to what they're normally used to in terms of how they design those fluidized beds for each of those 2 steps, but which have been able to happen very quickly. So it means we can jump from effectively, standing start to kind of, a couple of thousand tons of installed capacity in about 2 years. The second bit is energy efficiency. So the materials we use are very thermodynamically efficient. Typical issue was about the speed of capture, and sort of fluidization helps overcome that. So energy wise, flip forward onto this slide. So for the pilot systems, which is the bar on the left, our target energy efficiency is 1.5 megawatt hours a ton. There'll be slightly over spec, but to be able to operate at slightly higher than that. But over the life of those pilots, the aim is to be that, and maybe even below. Then for the first commercial facility, we're looking, we think, based on the learnings from those pilots, we can get that down another 15% or so call it 1.25 megawatt hours a ton, and the levers to do that, and then to drive it down even further at scale, where we think we can hit below a megawatt hour, call it over the next 5-6 years or so, are really about mechanical designs. It's minimizing pressure drops, it's improving heat recovery systems, which is sort of, how do we integrate, again, quite well understood, sort of mechanical designs in other industrial contexts into the design of the units. And then it's a material science lane as well, which is about improving the sorbent, and it's the energy sort of required to deliver on both the capture and particularly the calcination stage. So yeah, I mean, combining, obviously the energy is the major component of OpEx. So if we really push down the CapEx and push down the OpEx, then it ultimately does feed through to a lower cost, which we think is really a way to kind of further push DAC out and quickly scale it up. And I kind of put a number on that. The pilots, we think, will operate at sort of well below $400. And at least from our bit, the sort of technology bit, again, we're talking about sub 70 for the capital equipment. And really then a lot of it comes down to what's the price of storage and what's the price of energy. And I think that speaks to challenges that the sector as a whole really faces. How can you get low cost clean energy, and how can you get the storage that is needed to help scale up for the sort of capture technologies. And then we think the first commercial facility, our target will be below $300 in terms of the core kind of costs, leaving aside their marketing and some of those other costs, but core kind of costs of operation levelized over the life of the project, but sub 300 is the target. So yeah, I mean, maybe just jumping on quickly to the milestones. So the second one here is the 1,000-ton pilots with those two commercial partners, including Deep Sky that we've mentioned, which we're targeting Q3 is when they will both be operational. Before that, we've got a 60-ton pilot in the north of England, a place called Teesside, which is one of the major industrial clusters in the UK, where they're planning to deploy DAC and a whole bunch of other things like resource capture, hydrogen, etc., sort of low carbon clusters. That is really exciting. The first bit of that, actually, the carbonator goes in next week, and then during Q2, the sort of rest of it, including the calciner, will show up. So we're sort of operating at pilot scale, doing pilot scale testing, really already from about next week. And then sort of there's also obviously things that we're working on kind of longer term beyond these pilots, including our own kind of first commercial facility that we'd like to have operational by end of 25, beginning 26 at the latest. So the sort of other key milestone for us is prepping for that through completing kind of front end engineering design by the end of this year. So yeah, hopefully that's a helpful summary, and happy to, I guess, have a discussion at this point.
That was great. Thank you very much. A lot of exciting numbers in there. I wish people who talk about DAC on the internet could see some of these numbers. But yeah, so that's super, super compelling. Would love to start where did the idea come from? What was the inspiration for using fluidization and the Airhive approach, and talk about that, and like, how did the idea evolve in advance? How did you guys meet? How did the company form? Would love to hear a little bit about the sort of origin story of Airhive.
Jasper, do you want to?
Yeah, so Rory actually reached out to me. I think he found me through my research group, but reached out to me on LinkedIn. So my PhD, which I'm still finishing up at Imperial at the moment, is in industrial decarbonisation. So I work in the FENL group, clean energy group, where we do a lot of work on fluidisation, high temperature CCS, hydrogen-based processes. So I had a lot of, I guess, research background in fluidisation, and when Rory came to me, we got sort of speaking about DAC, which I think we're both, knew was a really important part of meeting the climate goals, and started working on a few different ideas. I think my research background, I operated fluidized beds, done a lot of modeling of fluidized beds and chemical reactions with gases and solids, metal oxides similar to the ones that we're using in our process. So I had sort of seen firsthand how quickly fluidization speeds up chemical reactions between gases and solids. And I think that influenced, the driving force behind using this as a sort of technology that could really speed up the capture rate and bridge that gap between enhanced weathering and DAC. Create that the speed and control of direct air capture, but some of the really favorable energy and non-toxicity, widely abundant minerals that are prevalent in enhanced weathering. Rory, I'm not sure if you have any other points there.
No, I think that's right. I mean, I think there was the idea was sort of mulling away in the back of Jasper's mind. We spoke at the beginning of sort of January 2022, and I was sort of finishing a climate and energy degree, kind of having gone back to school basically part-time and sort of work, let's say, working through some other ideas about DAC, and then we spoke again in kind of June of 2022, Jasper and I, and had a couple of other people involved right at the very beginning, the sort of, I think Jasper's initial instinct was the one that we kind of followed most of all, and I think it's been you take a leap of faith as a non-technical person, and you sort of I'm not an engineer by any stretch of the imagination or a material scientist, and I think it's been a kind of joy to watch, as we had all these things, we're like, oh, here are the challenges, and to see actually how quickly a lot of them fell away, and every time there was an uncertainty range about whether we'd need to do something like heat the air on the input, and it was like, oh, that could be completely killer, that could totally kill the approach. Proved that wasn't the case. So anywhere where there was uncertainty, it seemed to come down at the favorable end of the range, and the sort of speed at which some of those early identified risks kind of fell away was it was fantastic to watch. And so where the idea really is Jasper's. I guess I'm just along for the ride.
I think Rory's being very humble. He was quite often the driving force to make sure that some of those technical risks were easy for me to be in my academic land thinking about some of these problems, but Rory really applied the sectorial knowledge, as well as making sure that this is an economically viable process, as well as technically deployable right now.
Very cool. Well, thank you for sharing that. I'm hoping the scientists and the engineers in the audience will ask some questions about fluidization, because I don't really understand it, but I also don't really know what to ask. So I'm going to move on to the sorbent. In your Frontier app, you say the sorbent combines metal oxides, carbonates, and salts. I assume it's a proprietary material. I don't know what more you could say about that, but could you talk about anything additional you can share about the sorbent? Does the process use up the sorbent on a certain level, and does it have to be replaced? How much sorbent do you need per ton of capture? Maybe a little bit more discussion there would be helpful.
Yeah, right. So we've got a material science sorbent development pathway going on in the lab that's ongoing. So that we sort of give a broad mixture of materials that we're exploring, and the exact sorbent recipe is evolving every day. So we're testing out new methods that we think will be more sustainable, cheaper, lower energy requirements. So that will be constantly evolving in our R&D pathway. But our base minerals that we explore, which are some of the cheapest minerals on Earth, some of them are the sort of sorbent losses in the system. So you get some particle breakage when the fluidization physical process happens. So we have gas solid separation systems on our reactors or machines, which essentially captures those losses through like filters and cyclones. So industrially available equipment, and we're then working on repelletization methods, so resynthesizing those back into the kind of particle sizes that we would use to re-input them back into the process. So there's a few different routes that we're exploring. So one of which is the repelletization, and then the other, which I think is quite interesting to talk about, is when the minerals come out of the system, as they're collected, the lost particles, they actually come out in the oxide form. So they come in as a carbonate, they come out as an oxide, and a lot of energy is used in industries like cement and iron and steel to create oxides as key inputs. So we foresee that at large scale, there is potential to actually sell those oxides into industrial supply chains. And we're not doing that for these pilots, but think that that's an interesting avenue to explore at larger scales to make sure that material extraction requirements are really minimized and hopefully eliminated. That's the purpose of the repelletization approach.
Yeah. And so just to reinforce, it's not for cost. It's the sorbent at even now. But certainly its scale is like less than $1 per ton of CO2. We're talking about very, very low cost, hugely mined such sort of carbonate minerals so you sell the oxide, maybe you make a small amount back, but really it's about reducing the sort of any excessive need or sort of reducing any additionality in sort of mining requirements. And so even if you're operating at certainly megaton, even gigaton scale, the sort of net additional requirement, if you were to sell it all back, would functionally be zero, because you become simply a sort of intermediate stage on an existing material supply chain that already goes to construction of buildings at massive scales. So if you just use the sorbent, use it a bunch of times across maybe 100, 200 cycles, and then you sell it in the oxide form, which may have a small decarbonisation benefit, but really has a kind of circularity, primarily kind of circularity benefit.
Got it. And maybe this is a stupid question. How does the sorbent, is it still in a fluid? Does the sorbent moves from the carbonator to the calcination reactor? Is it like in a fluidized state when it moves? How does the loop physically happen?
Maybe I can just say,
Yes.
to disentangle fluid, and so the use of the word fluid is a way to describe not that it is a liquid. So it is a solid sorbent, right? And fluidization is about that blowing of gas through a bed of particles so that they take on the properties of a fluid, like air is a fluid. When they come out and they're transferred across, there are kind of quite well understood. Just you would then, as it comes out, then it returns to a kind of just a static, solid like bed of particles, and you could either convey it through blowing it through, or you can just have sort of manual conveyors, and that's something. Jasper can speak further about that. Yeah, I know the language around fluidization is does immediately make people think about liquids or solutions or things like that, but it's maybe not overly helpful as a sort of process description.
Yeah, so how does it?
Maybe just to add to that, we're exploring a few different ways of solid transports between the two systems, but fortunately they're based on fairly well established methods from things like metal processing, cement and iron and steel industries for moving sort of powders and particulate matter. But things like screw conveyors, pneumatic transport systems. So pneumatic transport is what we discussed there about blowing gas through particles to move it that way. So there's a few different off-the-shelf methods that we're looking at for that, and we'll do different ones for different pilots is the plan.
Sort of thing you'd have in big mining operations, in a sort of similar sectors, wherever they're moving large amounts of solids between different stages of a process.
So it could be some species of conveyor belt, or it could be some species of like vacuum tube or pneumatic tube, depending on what becomes most techno-economically sensible.
Exactly. Yeah.
And I think there are a couple of follow-ups on the sorbent in the Q&A, and everyone please feel free to continue to put questions in the Q&A, and we'll get to those in a few minutes. So your form factor, again, I'm pulling from the Frontier app, which I put a link to in the chat. So you have, there are 8 carbonators for every calcination reactor, and that's kind of a module for you. Is that correct?
Yeah. So that is, yeah. So we have essentially the calcination, which is very quick. So the removal of CO2 from the sorbent at 800 degrees is very quick compared to the carbonation reaction. While the sort of thesis behind Airhive is to have very fast carbonation, but it's still dealing with dilute concentrations of CO2 that are at 400 ppm. So the time for the sorbent mineral to actually convert from unreacted or unsaturated with CO2 to then being fully saturated takes longer than the calcination, which is simply releasing the CO2 from the solid material. So that's the sort of reasoning by having 8 carbonators versus 1 calciner in terms of the material or solids throughput of 8 carbonators, because that is taking a bit longer than the calciner. You have 8 feeding into one calciner. The alternative to that is having a smaller calciner attached to a carbonator.
Got it. And so kind of what I'm trying to get is this module of nine containers, like what if I or however you want to present, like what is a module of your system, and how much CDR does that module deliver per year, and like what is the land footprint of that module? And I'd love to like scale that up to a bigger facility just to understand.
Yes, we're at about 1,000 to 1,400 tons per year for a shipping container module carbonator system. So that would feed
at
into
least that's the sort of
calciner.
target, right? That's the next iteration beyond those pilots. So those pilots are about the footprint of a shipping container, on those axes, but higher because of the filter. So we look to optimize that down into a shipping container, and it will end up being somewhere between 1,000 to 1,400 tons. Now, whether that is then paired with a small carbonator and then that becomes the module, or you have a bunch of those into a full shipping container size calciner is an open question. I think our default assumption had been the latter, but that sort of 8-to-1 or whatever that exact ratio is will depend on what the size of the carbonators ultimately prove to be. But those are sort of 2 different pathways that were actually maybe now a bit more of an open question than they were last summer when we put in the frontier application.
So it's roughly 1,000, like just thumbnailing.
Yeah, call it 1,000 tons, something like that. Yeah,
and that's for the capture. So like if we scale up to, I don't know if you have these numbers in your head, but like a megaton facility, I think this might have been from your app as well, but 715 carbonators and 180-ish calcination reactors. And like, what is the land footprint of a megaton facility?
Yeah, actually, we had a look at this recently. It's in the order of a few hectares. So anywhere from 2.5 to 5 hectares, depending on how much sort of contingency you want to put in there. But that's sort of order. So we think that that's because of the capture rates. So the fluidisation means you have very large volumes of air going through a small cross-sectional area, which is good for capex, but also good for actual land footprint as well. So we think that that at that sort of size, it becomes quite small compared to the energy, the footprint with energy that you might need. So then it becomes a question, how can we really minimize energy requirements? So that's also something that we're working hard on as well.
Got it. And the spacing of the modules, is there an issue with the CO2 depleted air is coming out the top? Do you have to you don't want to obviously recapture that air? So is there any issue with spacing to make sure that you're not, is that a site design consideration?
Yeah, that's definitely a site design consideration. So actually we're working with an engineering design firm to answer some of those questions at present, but yeah, still ongoing work, definitely.
Got it.
I think that's one of those interesting questions that is almost, could be transferable knowledge across the DAC sector. Obviously, there'll be differences in the way that fan layouts will be for different DAC approaches, but it's definitely maybe some missing information, and maybe even in the academic sphere that we're interested in contributing to.
Got it. So on the energy requirements, thank you for sharing those, and they're super impressive. And I would also just point out to, again, all the people on the internet who say DAC costs $1,000 plus a ton. I mean, your very small scale pilot, your price in your Frontier app was $530 a ton. And I think there's a lot of innovation happening across DAC, including with you guys, to get costs down and energy requirements down. Do those numbers that you shared include air handling and CO2 compression, or is it simply for capture? Like, what do those numbers include?
Yeah, so the 530 number, which was the price we sold to Frontier at for our first commercial facility, that included the whole shebang. So they've got quite a comprehensive techno-economics, including compression, storage, as well as MRB, some contingency as well. Was there anything else I missed on that, Rory?
No, registry fees and a fat kind of uncertainty discount, which is, you know, a really sensible approach. And as a sidebar,
Yeah, I meant
the frontier application makes you smarter, is what I was going to say. But yeah, it is the whole thing.
The energy requirements that you quoted, the 1.5 megawatt hours descending to below 1 megawatt hour per ton, does that include air handling and CO2 compression, or is your slide? Okay,
and roughly speaking, it's like 10% carbonation, 80% calcination, 10% compression, like post-processing. That's a sort of rough breakdown.
And air handling is part of the carbonation?
Yeah.
Yes, exactly.
Exactly.
Yeah. So
that's one of the real benefits of. Yeah.
Sorry, Roy.
Yeah, I was just going to say, it's one of the real benefits of the fluidized bed is the fact that there's very low pressure drops. So you know, and that was maybe part of Jasper's, let's say, important inventive leap, in that typically when people think about fluidized beds, you think about more like cylindrical things, big tall columns, which have these really deep, you know, beds of particles, meaning you have loads of particles, like a, you know, big tube, like filled up quite high with the solid materials. In our case, we've taken a very unusual kind of niche design of a fluidized bed, which is wide with a very thin bed, and all of that is about to reduce the resistance that the sorbent gives to the air that's being pushed through, meaning pressure drop. And pressure drop is effectively directly proportional to the energy that goes into the carbonation step. So the amount of carbonate, the energy that goes into the carbonator is extremely low, because we are minimizing pressure drop by this kind of unusual fluid bed design.
Got it. You don't mention this in your Frontier app. It's a little bit, it comes up, it's coming up increasingly, I would say, when people talk about DAC. For example, Avnos announced their fundraise today, and they assert that they capture 5 tons of water for every ton of CO2 that they capture. So they're actually water positive. Does your process require a water input? And if so, how much per ton?
Yeah, so we're estimating about 0.6 liters, cubic meters per ton. So 0.6 liters per kilogram. Let me just make sure I've got that right.
6.
Yeah, sorry.
And that's
0.6 tons
of
sorry. Yeah, 0.6 tons of water per ton of CO2. That's the very uppermost limit. So we expect any sort of ambient humidity to decrease that requirement significantly. So if we've got no humidity in the air, we need to add some moisture, and that's about 0.6 liters per kilogram of CO2, or cubic meters per ton of CO2.
With the sort of potential for it to drop to 0 if you have 100% relative humidity outside. That's the sort of
your process would be favored by a more humid environment.
That's right. Yeah. But you know, the use of the closed system, just like with some of the heat, sort of the energy side, provides for quite high amounts of water recovery. So that is the sort of supplemental amount that, you know, that remains. So you put in more at the start, and you keep a lot of that in the, you know, in the core system. Yeah.
Got it. And pardon my ignorance, but 0.6 cubic meters is 0.6 tons or not?
Yeah, exactly. So yeah, the density of water is about 1,000 kilograms.
Sorry. And we did an estimate. I think it was, you know, you're talking about, you know, it's relative to say, I'm not going to get this right. It's either megaton or gigaton scale that you'd be talking about the amount of water that's used by a medium-sized nuclear reactor. I think it's gigaton scale. Yeah. I need to, don't quote me. On this public video.
Yeah, no, I got you. But thank you for that. There are a couple audience questions about what you're going to do with the CO2, which obviously is an important point. So I'm going to leave that for the audience questions. I'd love to ask a little bit. I mean, what Deep Sky is doing is, I think, super exciting and important for the sector in terms of advancing companies like yours, and giving you a place to deploy. And I put a link to that in the chat. Can you talk about, in terms of looking at Airhive and what your future, do you see yourselves as a project developer, or do you see yourselves as a technology provider to other project developers, or somewhere in between? Like, how do you see your scaling path working from that perspective?
Yeah, I think our operating assumption is that being a technology provider in the near term, let's call it this side of 2030, is a really good way to get the deployment out quickly. You know, like it's So with Deep Sky or with any other sort of project development partner, and it might be for DAC plus storage to sell credits. It may also be for industrial decarbonisation, or as providing a source of low carbon CO2 relative to a fossil source, source of CO2 for e-fuels or other utilization pathways. I think partnerships with project developers are going to be really important and exciting. I think we want to also be a project developer, so we are planning to build our first, build an operational DAC plant next year. What the precise form of that, we're still scoping. We may have partners, but be involved ourselves in project development, I think is important. I think that's important because we want to, not be at a step removed from agitating for increasing the amount of credits that are bought. I think that's a crucial kind of sectoral level challenge that you have to sell credits to feel the pinch point, and therefore really push, kind of collaboratively with everyone else. And then I think, I think developing large, project facilities, over the medium term is something that we're interested in. But we see it as a way to, being both of those things as a way to kind of accelerate out the technology into the real world as quickly as possible.
Yeah, definitely agree. It's not either or. What you are now and what you are in 2035 could be different kind of. Yeah. Last question from me, and I put a link of this to the chat. There's a tremendous amount of innovation happening in direct air capture. I think it's like direct air capture is not one thing. It's many different approaches. I think RMI broke it out into 10 or 12 approaches in their recent applied innovation roadmap. And I'll put a link to that in the chat as well, because it's really amazing. But our friend of the show, Grant Faber, just published a list of DAC companies. It's like 130 and growing. I think my list is, Jason Hockman at DAC Coalition has a list of 150 or 180. So there are a lot of DAC companies out there. There are a couple of large, I would say, it's hard to say anything's an incumbent at this point in the CDR sector, but the large companies that have been heavily resourced, Heirloom, Climeworks, Carbon Engineering, now acquired by a fossil fuel company, that have hundreds of millions of dollars of capital and are basically acting as technology developers and project development entities. How does a company, with a great idea, innovation at your stage, how do you see the competitive landscape? And on a couple of different fronts. I mean, you have the equity financing. I've heard that early stage direct air capture companies are having a hard time raising equity capital because the people that invest in these things have already have their DAC investments and don't necessarily want more DAC investments, which is kind of a problem. Raising project finance. Again, Deep Sky has been amazing. And Deep Sky has, I think, 6 or 8, maybe more, direct air capture 1,000-ton deployment partnerships. And then credit sales. Like, how do you differentiate yourself in the marketplace when you're trying to get people to buy your credits? I mean, this seems like we need the innovation, but the DAC, it seems challenging a little bit for early stage DAC companies to address the competitive issues on each of those fronts. How are you guys doing it? How do you view it? Any thoughts on that?
Yeah, I mean, I would say the first thing is like that it's important for us to not take our eyes off what is the ultimate goal here, which is, a collective effort to try to reach, the amount of removals that we need from a Earth system perspective, let's say. So, I think you often have it, waves of innovation. We're sort of riding a wave of removal innovation, DAC innovation. And overall, I think it is absolutely it's not even close the massive net positive that it represents to have so many people out there and innovating. And, so I think like that's the sort of first big picture, the way we see it. I think, for us, we are really excited by some of our partnerships, both on the storage side, our own plans, and then for some of the utilization stuff that we're working on as well. I think there's important decarbonisation opportunities there, which helps diversify some of the kind of, the market risk, revenue risk. I think fundamentally what kind of matters is, for any successful business, I suppose, certainly in our field, is inherent technological advantage and speed of deployment. Getting to revenue, getting to commercializing quickly, and I'd just say we feel good about sort of both of those things. But if we ended up not surviving, and the knowledge was out there that ultimately we're beaten by another technology or a range of technologies, and we think there's plenty of room for the multiple companies to exist and to survive and to thrive kind of over the next decade and beyond, given the scale of the challenge. But if ultimately it didn't happen, that will only be, I think, because someone has come up with something that is fundamentally better, and that will that's a public good fundamentally. So that's, I guess, the way we think about it.
Great answer. And hopefully we see, and your price point will help with this, but hopefully we see buyers willing to diversify beyond Airland and Climeworks and Carbon Engineering when they're buying DAC tons. And we do have some investors on the call. So
well, I think catalyzing kind of we're hoping that once we get those pilots up and running, that to be able to demonstrate lower costs even at pilot scale, we see it as important, partly to change the narrative, right? I mean, there are people in the climate science community who do amazing work, but there is a debate that goes on about, would we ever see DAC below X dollars a ton, right? And, I think innovation is a crucial way of helping change some of that framing. I think that'll feed through into the academic community, feed through into the policy community, and maybe, help kind of tamp down some of some of the skepticism about how much we will be able to deploy and at what scale, and how much it's going to kind of cost, total economic cost for countries, the planet, etc.
Well said. Megha, do you want to come on and ask some audience questions?
Sure, yeah. We've got quite a few. I think we had a couple of questions on power requirements. So could you just quickly go over what the power requirements are today and where you think it'll end up, but also a little bit about how that breaks down between the fluidization versus calcining or anything else?
Yeah, sure. So we're targeting about 1,500 kilowatt hours per ton for our pilot systems in Q3. So at the moment we've got a lab prototype. So the measurability of that system wouldn't be representative of that sort of pilot scale energy requirement. That is mainly broken down into, as Rory mentioned, about 10% on the fluidization or the fan energy, the carbonator, so providing the air to the system to capture the CO2. About 80% on the calcination or the regeneration of the sorbent to desorb the CO2 from the sorbent mineral, and another 10% roughly for compression and storage. So that's the main energy profile. The process uses entirely electrical components, so it can be based off renewable electricity. So the project in Canada is based on hydroelectric power. So that's something that we think is really important for DAC processes to be able to really decrease pressures off fossil fuel systems.
There's an interesting point, Megha, maybe we'll just add to about sort of how you can use energy. So we've done some modeling, and we're sort of looking at this in a couple of sort of specific deployment contexts about what would happen if you could be based, say, purely on quite low capacity factor renewable energy, and we if including maybe that was only used otherwise curtailed renewable energy, if there is if they would be curtailing, and the benefit of having quite a low capex system is one thing you can do is just oversize the capital equipment, operate more when the energy is available, and then turn it off. And we were sort of surprised, I think, by some of the positive numbers about what you'd need. If you have a relatively low capex system, it doesn't hit you too much, and what you really just need then is to have a smaller drop in the energy price, which is sort of available if it was effectively otherwise lost, a curtailed energy that you can then use. You can sort of drop the energy price and still get a very attractive cost per ton. So that's something we're sort of pretty interested in, and something we'll be factoring in some of the sort of scoping work we're doing about the sort of early commercial facilities.
Yeah, exactly. Okay. I think using curtailed electricity is a super smart way to go, and it makes sense with your process. So that's great. Someone also asked specifically on, and I don't totally understand the technical aspect of this, but maybe you will, with respect to the fluidisation, is a lower density sorbent a possibility? And I think they mean with respect to potentially reducing energy consumption. Does that make sense? Are you able to answer that?
Yeah, so it's a good. I think the person asking the question must be familiar with fluidisation. So the pressure drop, which is related to the fan energy requirement, so how much energy you need to blow the air through the system. The pressure drop is the weight divided by the cross-sectional area. So for a given reactor size or vessel size, if you have a less dense sorbent, you've got less weight, so therefore less pressure drop. So that would, that's one factor that would reduce pressure drops. But you also have to think about what the CO2 uptake capacity is. So if you have a lower density sorbent, perhaps a fizzy sorbent might be one option. You'll be capturing less CO2 in sort of the capacity of the material. So it's one factor, and it's an important thing to think about. But it's only one sort of parameter within a whole space of energy characteristics that we have to think about. So we're going down the path of natural minerals, which are widely abundant. They've got very good energy properties. They're non-toxic, and they chemically bind with the CO2. So it means that they have a lot of CO2 that they capture or chemically bind in one cycle, which means that the overall process works very well with them.
Got it. Okay. And then, yeah, just another fluidization related question, which again is beyond my technical expertise. But they asked, the pressure balance is operationally very challenging with fluidization, and reversals can happen and be very damaging. Curious what would happen in a reversal.
I'm not sure what reversal means. If it's referring to perhaps particle losses, so we've got gas solid separation systems, which means that the particle losses are captured in filtration and gas solid separation systems, such that losses are fitted to codes and regulations for the local jurisdiction. So yeah, in terms of any reversals in the system, we have some mechanical aspects of the design which controls where the air flows and where particulate matter flows, which makes sure that we have the material in the regions that we want them to be. And I think that sort of engineering design would be a lot more difficult if there weren't very well established manufacturing partners that we've been working with that have been building fluidized beds for a whole variety of applications over the past few decades. So things like drying, spices, salts, cement, iron, and steel industries. There's a whole wealth of manufacturing expertise out there that we've been really lucky to leverage in our engineering design work.
Got it. Okay. Hopefully that answers the question. And then someone also asked, what percent, if you know, what percent of air CO2 reduction is achieved per pass through the system?
Yeah, so we're very close to 100%. So some of the lab readings we get in an everyday experiment would be fluctuating between 0 and 10 ppm. So we sort of say in most of our conversations close to 100% removal. But yeah, it really is sort of at that sort of 99% range.
Okay. Yeah, great. All right. And then I know Toby said he was going to skip asking about the sequestration, but a couple of people did ask, what are your plans for sequestration? Do you need to transport the CO2 to where it's going? And, maybe in the context of the Deep Sky partnership, as well as just thinking about the future as well.
Yeah, I mean, maybe can say, like any other DAC, even though it's a modular system, the plan would be to locate as close to, you really need sort of two things. You need clean energy and you need a place to store the CO2. We're sort of scoping at the moment potential locations for our first commercial facility, and those are the central two metrics that you need to, the central two things you need to tick to demonstrate basic viability of a plant. And then obviously you've got things like price of the energy and any sort of fiscal subsidy or whatever might come in on top to make the project more attractive. So yeah, I mean, sequestration, I think there's an interesting kind of wider point here about the way it's evolving. You've got a bunch of really exciting kind of mostly mineralization focused storage sort of startups, and then you have lots of big kind of government regulated, often sort of CO2 storage sites, which are not mineralization, they're like depleted oil and gas fields or saline aquifers that are often commissioned or developed by energy companies. And one of those, sort of the startups are themselves often still in a sort of technology development process, and maybe more suitable for first commercial facilities for like sort of that company planning for a first commercial facility. And the big kind of storage sites are more typically talking about megatons per annum, and often linked into point source capture, sort of in decarbonized clusters. It's true in the UK, but other places too, where if it may be like carbon engineering, you plan to jump to megaton scale, at which point you can sort of do that. But most tech companies, I would say, are not planning to do that. Jump instead to sort of kiloton scale, whatever the number of kilotons are, but certainly sub megaton. In which case, often you are competing maybe through a government run process that says that you're a mouse compared to these large elephants of point source capture kind of companies that will be looking to sequester or to take up some of that pipeline capacity. So I think there's we would love to see a bit more government run or sort of innovation friendly or startup friendly sort of government policy that said, okay, in these big megaton scale storage developments, we are going to reserve capacity at the 0.1 megaton, 0.2 megaton for sort of early stage stack companies who could bear about that level of a sort of commercial sort of off takes. And I think that's where Deep Sky comes in as a fantastic kind of middle ground between those sort of different ends of the spectrum. So more of that, whether it's startups or government run sort of processes, would something we'd be really keen to see.
Yeah, that's a great suggestion. Well, guys, thank you so much for joining us. I think we're out of time, but this has been really great and exciting to hear what you're working on. And yeah, Toby, over to you.
Awesome. Thank you, Megha. And thank you to the audience for the great questions. Rory and Jasper, thank you so much for being with us. Super exciting to learn more about what you guys are doing, and very impressive. A lot of your numbers and figures and scaling plans. So look forward to seeing what the 2024 and 2025 bring to Airhive.
Yeah. Thanks, Toby.
Thank you so much for hosting us.
Thanks for having us.
Our pleasure. Thank you so much. I'm going to share my screen really quick to talk about what's coming up next from a programming perspective with us. And I put a link in the chat to our Luma page where you can register for all of these things. Next Monday is a carbon removal challenge check-in with the Open Source Hardware Association. OpenAir co-founder Matt Parker is running the show here. It's super exciting program to get university and college students to develop CDR research projects. And the winners will be flown to New York to present at the eve of the Carbon Unbound conference in May. So check that out to learn more about what's going on there. And on This is CDR, we have a great run coming up, a few more to add, but next week, Alkali Earth, which is a fellow summer 2023 Frontier pre-purchase cohort mate of Airhive, and basically alkaline materials, storing CO2 and alkaline materials that will be put into roads. Super interesting. Dan Maxbauer and Sean McCauley will join us to tell us more about that. So again, you can register via the link in the chat, and look forward to seeing you then. Thank you for joining us. Thanks again to Rory and Jasper, and everyone be well, and we'll see you next week.